So, factorials again. Brilliant, because if there's anything you desperately wanted today, it's more factorials explained slower and simpler, as if you haven't suffered enough. Today we're bravely dragging ourselves through factorial calculation with something as painfully basic as if-else logic. You know, that decision-making powerhouse that makes choosing pizza toppings feel like advanced calculus. Now don't pretend you're not secretly thrilled. Oh yay, more conditions, exactly what my life was missing. But here's the reality check. If-else logic is what computers do best, just a tedious stream of yes or no questions until you eventually give up and switch your career to pottery. Why factorials though? Well, apparently maths isn't content just multiplying numbers. It wants to feel special by pretending it's making critical decisions along the way. Because factorial calculation desperately wants you to think it's complex, even though it isn't. It's the maths equivalent of ordering tap water at a posh restaurant and being served with dramatic flair. Ah, recursion. The maths equivalent of narcissism. Imagine being so obsessed with yourself that the only way you can define who you are is by referencing yourself repeatedly, like a reality TV star name-dropping themselves in third person. That's recursion. And factorial recursion is peak vanity, a number defined as itself multiplied by a slightly smaller version of itself. Shocking innovation, I know. Let's break this self-absorbed definition down. If the number is 0 or 1, the factorial equals 1, because mathematicians enjoy making arbitrary rules while stroking their beards. Why 1, you ask? Probably because they ran out of coffee, patience, or both, and just agreed to get on with their lives. For numbers above 1, factorial arrogantly declares, I'm myself multiplied by factorial of myself minus 1. This continues until it gets bored and finally admits that factorial of 1 is 1. That's it. That's the revolutionary maths idea they're teaching you. You're welcome. Now, let's awkwardly translate this pretentious maths into equally pretentious pseudocode. Or what's pseudocode, you ask? It's what programmers write when they want to pretend they've done some work without actually coding anything. Here's factorial recursion in pseudocode terms. That's literally it. 2 lines. It's the coding equivalent of opening instructions on cereal boxes. Pour cereal, add milk, groundbreaking stuff really. Now, because learning apparently requires making things complicated, let's painstakingly walk through factorial of 4. Why 4? Because it's small enough to manage without your head exploding, but big enough for factorial to feel important. We start at 4. But factorial immediately panics and asks, wait, what's factorial of 3? But of course, factorial of 3 doesn't know either. It awkwardly asks factorial of 2. Factorial of 2, equally clueless, bothers factorial of 1, who finally ends this pointless chain of confusion by smugly announcing, I'm 1. Then, and only then, can we go backwards, putting everything together like some irritating jigsaw puzzle you never wanted. Brilliant, we've cracked the simplest puzzle ever. Maths is really pushing limits now. Congratulations, you've survived factorial recursion, maths' least efficient way to multiply numbers. Now recursion seems harmless, cute even, but your computer secretly hates it. Every recursive call, factorial asking factorial of a smaller number, gets stacked up in memory like a frustrating pile of unpaid bills, each waiting anxiously for the previous one to finish. This call stack, as it's technically called, quickly grows tall and wobbly, like a game of mathematical Jenga where every block is another unresolved multiplication. Unlike those awful Fibonacci numbers that create exponential nightmares, factorial recursion thankfully stacks calls linearly. It's just one call waiting behind another, like being stuck in a painfully slow coffee shop queue, knowing there's no hope until the front person finally gets their overly complicated mocha, frappa, whatever. And only once you hit the base case, the simple coffee order at the front, can each call finally resolve its issues one by one, returning their results upwards. Lovely stuff. Recursion, really efficient. Let's talk efficiency, or as your computer calls it, can we finish this already? Recursive factorial isn't terrible. It doesn't redo calculations like Fibonacci, meaning it's not completely evil. It just calmly counts down, creating exactly one call per number. But here's the bad news. Your computer still dislikes recursion because every call takes up memory. For small numbers, no big deal that. But ask your computer to calculate factorial of a huge number, and it will react about as calmly as you would if asked to juggle flaming chainsaws. You'll face a stack overflow, which is a fancy tech phrase meaning your program crashes spectacularly. In short, factorial recursion is efficient enough to pass basic exams, but not trustworthy enough for serious use. It's like the mate who promises to help you move house, shows up late and spends most of the time texting. Not exactly reliable under pressure. Yes, recursion is annoying, but, and I'll deny ever saying this, it's genuinely useful for learning. Pretty solutions aren't always the best solutions, much like designer shoes aren't always comfortable. Tough truth. Quick snarky recap before you forget everything. It's predictable but still annoying. Efficient enough to brag about at parties, not enough for real-world use. Tired of recursion hogging your computer's precious memory? Good, because next we're introducing iteration, specifically factorial using a trusty old while loop. Your computer will thank you, your memory will thank you, and you'll thank me for ending recursion's self-absorbed reign of terror. Credits, script by your name. Narration by narrator's name.